right, questions? I only got 22 Git repos for PA4, which is better than the 7 I had a few days ago, but half of you or the other section have not turned in, have not made a repo that's accessible to me, so please, please, please do that before tomorrow morning at 8 o'clock. All right, PA4 is due 8 o'clock tomorrow. I will download the Git repos at that time. So make sure whatever you have to turn in, you have available then. So any last questions on PA4?
So I just want to make sure I have this straight. So the balance function just calls the height of root arrow left and root arrow right. That's it. It's just two lines. And then checks if they're equal.
No.
No.
Nope. So you got to do 3 things to know if a tree is balanced. You got to know that the height of the left and right subtree are within 1 of each other. And you have to know the left subtree is balanced, and you have to know the right subtree is balanced. So you recursively call balance on left and right, make sure those are both saying it's balanced, and then call the height function on left and right, make sure the absolute value of the difference is no bigger than 1. Okay, you got to have all 3 of those true to say the tree is balanced. Okay, and the case you're looking for in particular is something like this. Right, left and right subtrees have exactly the same height, but that's definitely not balanced. And the way you'll know that is when you call balance on this, it'll say this is not balanced. Because for this tree, the left subtree has a height of 3, the right subtree is -1. So make sure the heights are close, make sure the left subtree is balanced, make sure the right subtree is balanced. So it's like 4 lines instead of 2. Yeah?
So when you grade this, are you going to have several different databases that you're going to run on them for like different cases?
I was wondering about this last night.
Oh, okay.
I will probably run it on the main database just to see how it does with 1,000 nodes, and do some checks to make sure data is inserted in there. And then I'll build a database that'll probably have about 7 nodes in it, and load that in and actually look at the 3 traversal orders. Okay. And I'll make that database something where it's easy for me to know if the traversals are correct. And then I'll delete a root node and make sure the tree looks good, and I'll delete a non-root node and make sure the tree looks good. And that will probably be the bulk of the testing.
Okay.
And then I'll look at the code and look for all the comments and indenting and good stuff like that. Yeah? Make sure you can, yeah, so if you're getting exactly the same thing that the test program's putting out for your traversal is probably fine. Okay, same thing for height. I would make yourself a balanced tree and make sure that it tells you it's balanced. Because, you know, if you load in 1,000 nodes, it's probably not balanced. But if your balance is never working, if you've got a equals instead of an equal or something, right? So just make a small database with a balanced tree and make sure that that detects it. And yeah, delete the root of a tree and make sure that works, and delete a non-root and make sure that works. Delete a leaf, make sure that works. That's probably pretty good. Because deletion, as you probably know, it either works or it fails beautifully. Right? If it's not quite right, something pretty dramatic usually goes wrong. So if it seems to be working, it's probably a good bet that it works. Also try deleting like the last node of a tree. Make a tree with just 1 node and delete it, and then do your traversals, make sure it doesn't freak out. Yeah?
So this is kind of just like a weird question. While we're like running our code and testing things, and we have all of those like malloc things in there, and then we don't free them because we haven't written that function yet, is that causing problems? Like no?
No.
Okay.
Once your program exits, all your memory gets freed.
Okay.
So it's not actually causing a problem.
Okay.
Yeah. Yeah, that's the other thing. Make sure you run Valgrind and you're not getting memory leaks and you're not getting warnings while Valgrind's running. right, good to go. So let's go back to the knapsack problem, and let's talk about this in more detail. So the general statement of the knapsack problem is, you have a bag with a certain capacity, and you're trying to put things in the bag to maximize your value. And the bag is usually constrained by how much weight it can hold. So you have a table of like items, weight, and value of each item. And there's different ways to go about this. So if you're allowed to put in fractional amounts of items, then your algorithm is pretty straightforward. Load up with as much of the most valuable thing as possible. Okay, so if this is worth $2 a pound and this is worth $10 a pound, take as many pounds of this expensive thing as you possibly can. Okay, and if you only have, 3.5 pounds of this, take all 3.5 pounds. If you have enough of this to fill your bag, that's your best solution. Okay, nothing's going to get you a better solution. That's only if you're allowed to take fractional amounts, though. Okay, if you're required to take whole numbers of items, the algorithm gets more complex. So let me show you a sample table. So this is item, this is weight, and this is value. So item A weighs 1 pound and is worth $1. Item B weighs 3 pounds and is worth $6. And item C weighs 4 pounds and is worth $9. All right, if your bag can only hold 4 pounds, what's the best way to fill your bag? Just throw item C in, right? I could throw in one of item B and one of item A, that's 4 pounds, that would get me $7. I could throw in 4 of item A, that only gets me $4. I can throw in one of item C, that gets me $9. So that's my best solution. What about a capacity of 5? Yeah, I mean C is a clear winner. I could do a B and 2 A's and that would get me 7. I could do 5 A's, that would only get me 5. If I do C and A, I get up to $10. What if the capacity is equal to 6?
2 B's?
Yeah. 2 B's will get me $12, which is better than I do by taking C and then taking 2 A's. That only gets me $11. So we want an algorithm that will let us, for a given capacity and given weight table, figure out what the optimal way is to pack our bag with items. And for a fractional problem, if we could put in fractional amounts of these things, you can just say value per weight. And this is 1, and this is 2, and this is 2.25. So load up with as much of your most valuable item as possible. So you would put in, 1.5 item C's, and that would get you $13.50, which would be your optimal solution. Okay. For a fractional knapsack, what we're describing is what's called a greedy algorithm. So what do you do if you're greedy? You try to get as much money right now as you possibly can. Okay, that's what a greedy solution to this would do. It would say, wow, $2.25 per pound for item C. Give me as much item C as you possibly can until I either take all of it that's available or I fill up my bag. Okay, it's a greedy approach, and for a fractional solution, that works perfectly well. But for this integer version of the knapsack, where you have to take whole numbers of items, a greedy approach does not work. Because the greedy algorithm would say, okay, this is the most valuable, let's take as much of that as I can while I can fit one of those, and then you're left with 2 item A's, and you get a suboptimal solution. So we need something more subtle to solve this. And we can do it recursively. And it's not a bad looking algorithm. So let's define a function called maximum value, which takes an argument called capacity. And this function will return the max value we can get from a bag with capacity equal to cap. So you want to define this function. We feed it a capacity, it gives us back the maximum value we can get from that bag. So if we called max cap with 6, it should give us back a value of 12. Okay, well, it's going to be recursive, so we need a base case. The base case is if the capacity is less than or equal to 0, return 0. So if your bag cannot hold anything, then you can't get any value out of it. The most value you can get from a bag that doesn't hold anything is 0. Okay, otherwise, well, we're trying to fill a bag with items. We're going to start by putting some item in the bag first. We don't know which item. But if we have 3 items, A, B, and C, we have 3 possibilities. The first item we put in could be A, or it could be B, or it could be C. Okay, the order is not really important, but there's going to be some first item that we put in. So, case 1, well, this would be the case where we put in item 1 first. Okay. And if we put item 1 into our bag, here's what happens. First of all, we get the value of item 1. Okay, if we start by putting item 1 in our bag, now our bag has the value of item 1 worth of stuff in it. And the capacity of our bag has been reduced. The capacity of our bag is now capacity minus the weight of item 1. And what's the most we can get out of a bag with this capacity? Yeah, just max val of this. We add that to the value of item 1. So this is the value that we'll get out of our bag if we start off by putting item 1 in the bag first. We get the value of item 1 plus whatever we can extract from the remaining capacity of the bag. If instead we had started off by putting item 2 in the bag, we would get the value of item 2 plus whatever capacity is remaining after we put that item in the bag. The max value we can get out of that. And we simply return the maximum of all of those possible cases. So that's a very recursive way to describe the max val function. Basically, for every item in your inventory, calculate the following: the value of that item plus the max val of the capacity of your bag minus the weight of that item. Whichever one of those gives you the largest value, that's the max val for your original capacity. All right, so let's try that in this particular case. So our capacity is 6. So max val of 6 is the largest of the following. Well, if we put item A in, we get a value of 1, plus we've taken 1 pound away from our capacity, so max val 5. If we put item 2 in, we get a value of 6, plus we take 3 pounds away from our capacity, so it's max val of 3. And if we put item C in, our third item, we get 9, and we have 2 pounds of capacity left, so it's 9 plus max val of 2. So max val 6 is whichever of those 3 expressions is the largest. Well, max val of 5 is equal to, well, the same thing. Value of 1 plus max val of 4, or 6 plus max val of 2, or 9 plus max val of 5 minus 4 is 1. So we've got this recursive tree that's starting to blossom out sideways, right? This is all in the service of calculating max val 5. We need to find max val 4, 2, and 1. So max val of 4, well, it could be 1 plus max val of 3. Or it could be 6 plus max val 1. Or it could be 9 plus max val of 0. Everybody see what we're doing here? So if our bag can hold 3 items, we can put in item A first. It gives us $1 and leaves 2 pounds of capacity. We could put in item B, which gives us $6 and leaves no capacity. And if I follow this algorithm blindly, right, we could put in item C, which gives us $9 plus max val of -1. Well, we can't actually run that case, right? Because if our bag only holds 3 pounds, we cannot put item C in because it weighs 4 pounds. So when we iterate here, we have to make sure that we're only generating cases where the weight of this item I is not bigger than the capacity we're interested in. So we won't generate that case. Alright, so maximum value we can get from a 2-pound bag is either start with item 1, get $1 and add the capacity, the value we get from a bag with capacity 1, or if we were to put in item B, that's too heavy. Item C is too heavy. So it's really just one possibility here. So max val 2 will be 1 plus max val 1. And max val 1 will be the value of item 1 plus the value we can get from a bag that has no capacity. And now we're down to just edge cases. If the capacity is less than or equal to 0, we know the max val is 0. So this is equal to 0. This is equal to 1. Max val of 1 is equal to 1. Max val of 1 is equal to 1, plus 1 is 2. Max val of 2 is equal to 2. Max val of 3 is equal to 2, max val 2 plus 1, or 6 plus max val 0. Well, max val 2 is equal to 2, 2 plus 1 is 3. Max val 0 is equal to 0, that's a base case, 6 plus 0 is 6. Max val 3 is the largest of these, this is equal to 6. And I'm using dynamic programming here, right? So we calculated max val of 3 because we needed max val of 3. I also need to calculate max val of 1. I'm not going back and redoing this. I've already written down what max val of 1 is. It's a 1, so I'm just reading this out of my memory, right, my blue ink. So this is 1 plus max val of 3 is 6. 6 plus max val of 1 is 1, and 9 plus max val of 0 is 0. So max val of 4 is a maximum of 7, 7, and 9. That's equal to 9. All right, max val 4 is 9. Max val 2, I'm not going to recalculate. I'm just going to use my saved value as 2. Max val 1 is 1. Max val 5 is the maximum of 10, 8, or 10. So that's 10. And then max val 6 is 1 plus max val 5, that's 10. 6 plus max val 3 is 6. 9 plus max val 2 is 8. So it's the maximum of 11, 12, or 11. That's 12. And that's the value we got by doing 2 of our item B's. So this is exhaustively exploring all possible feasible combinations of putting things into our bag. And if we try to do this with a set of nested loops, it gets pretty combinatorially expensive pretty quickly. Because for a capacity 6, we could put up to 6 of these, up to 2 of these, and up to 1 of these. So we could make a pair of nested loops and try all those combinations, keep track of the maximum legal combination. But if you had 20 items, that's 20 nested loops. That's not going to finish in any time soon.
So thinking about bottom up versus top down,
Mm-hmm.
how do you make those decisions? Because obviously you can do it either way.
You can do it either way, but in this case, you know, my weights were pretty close to each other. If I had weights that were pretty sparse, I may not need to generate every single max val, right? Having a max val of 1 kind of forces that, but if my minimum weight was 3, right, I might only need to generate a third of these cases. So you could do it either way. I mean, you can go bottom up and just keep generating. That's going to be harder on PA5 because we're going to be working with a function with 2 variables to it. And it's not clear where you would go bottom up unless you start nesting loops again.
Because top down, in my, like, just from the little I've done, seems easier, like a little more
Yeah,
intuitive.
yeah.
But bottom up, I'm sure, has an advantage in some cases.
I'm not sure. I don't think top down is ever going to do worse than bottom up.
I like top down.
Yeah, yeah. Yeah.
So I did want to ask, you know, we were using the max function and just kind of putting in as many arguments as we needed.
Mm-hmm.
In actual C, is there a way to do that, basically, where you define a function that can have as many arguments?
You can, but you don't need to.
Okay.
So you can do something called var args and make a function that'll take an arbitrary number of arguments.
Okay.
But that's really hard to wire up a call to that because it depends on, you know, how your loop runs out. But what you're doing is you're iterating over the inventory of items. So first you generate this value, then you generate this, and if it's bigger than the first, set your maximum to this. Then generate your third. If that's bigger than your best, set your best to that, and so on. So it's just kind of a running max. All right, you can also keep track of your solution while you're doing this. We didn't do that here, but you know, this represents putting in an item B. This represents putting in an item A. This represents putting in an item C, right? And if I have my max value return, not just a maximum value, but also the inventory that gets me that maximum value, well, in this case, I can simply add a B to that inventory. That's the inventory for the max value of 3. And if this turns out to be my maximum value, right, this is an A plus whatever gets the max value out of a bag that holds 3 pounds. I take that inventory and I just add one more A to it. That's the inventory for max val 4. So you can work your way back up, and when you're done, you get the max val 6 is equal to 12. You can also get what the inventory of items is. And that's really easy to do on paper. It's a little trickier to do in code. But it's just, you know, mechanics of C and having things of variable length and passing them around through functions and defining structures and all of that stuff. But the concept is relatively straightforward. I mean, it's basically this. And if you draw this out as a tree, right, 6 branches down to 5, 3, and 2, and 5 branches down to 4, 2, and 1, and so on, you can see how this thing gets wider and wider as your initial capacity gets bigger. And so this is where the dynamic programming comes in and speeds it up. And so we can start thinking of lots of problems in this way. So here's a good thing to keep in mind. Repeated subcases. Okay, the reason that this is expensive is because, you know, max val 1 got calculated here and here and here. Max val 2 got calculated here and here and here, right? And for a more complex case, you end up calculating the value of this function for the same argument multiple times, okay? That's a really clear example of where dynamic programming will speed you up and where recursion will probably give you a good way to code an algorithm. The other thing, and this is almost necessary for a problem to be solvable, is that we can define the solution at some point in terms of the solution at other points, but this recursion has to somehow terminate. So if we could define max val of 6 in terms of max val of 9, 12, and 20, right, and then we try to calculate max val of 9, and it requires max val of 10 and 15 and 17, right, that recursion may never end. Right, this will end very definitely because all of the max val calls in here will have values less than the original one. And so worst case, you know, 6 times 6 times 6 calls later, these will be down to max val of 1 or 0, which will be my base case. And I stop recursing. But sometimes it's not clear that that's going to happen. Okay, so here's another example, rod cutting. So rod cutting problem, you have a new profession, which is you cut metal rods and you sell the pieces of them. This is your line of work. And you only cut pieces that are multiples of 1 inch in length. So 1, 2, 3, 4, 5, 6. And you have an initial rod of some given length, 6 inches, whatever. And there's a pricing table, which looks like length and how much you can sell it for. And so if you have no length, well, it's probably worth 0. And the uncut rod might be worth $20. But cutting it in half might be more valuable, right? You could get a 6-inch rod for $20. You could cut it in half, and it would be $10 for 3 inches. But you know, the act of cutting it in half for a customer is valuable, so maybe you can get $12 if you sell it as a 3-inch piece. And maybe nobody uses 4-inch pieces, so that's worth just a little more than a 3-inch piece. And maybe 1-inch pieces are really valuable, so they're worth $3 an inch. And so same thing, you want to know, how should I cut this rod up? You have an infinite number of customers who will buy whatever you have. How should I cut this rod up to get the maximum value? And in some cases, a greedy algorithm might stumble into the right answer, but in general, it won't. And so the maximum value you can get from a rod length equals the maximum where I goes from 0 to maybe 5 or 6 of value of I plus max val of length minus I. To go up to the length. Alright, so it's the same repeated substructure. Take the value of a 0 length bar plus the max value you can get from, in this case, 6 inches. The value of a 1 inch bar plus the max value you can get from 5 inches, and so on, all the way up to a 6 inch bar plus the value you can get from 0. And then each of these calls to max val is recursive. I guess we want to go to len minus 1. Actually, let's go from 1 to length, because I want this number to get smaller. And if all lengths are possible, that's a good description of the function. But if you only have some lengths, for example, if it's, you know, you're in a country where it's illegal to cut 5 inches of length, right, that may not be an option. And so, you know, it's like the knapsack problem. You have just this inventory table and you're trying to find the maximum value of this function. Really easy to code once you're past the mechanics of it, right? Really easy algorithm to write, and pretty hard to solve efficiently without doing something like this. Alright, still with me? Let's talk about egg dropping. So this is PA5. And I'll finish writing this up and post it on Canvas probably later tonight, but before class tomorrow. But it's easier to describe than it is to write. So, your goal is to make a function called egg. Egg takes 2 arguments, the number of floors and the number of eggs. And you're trying to answer a question, and your egg function is supposed to give you the answer to this question. Okay, so here's the question. Here's the first question. You have a collection of eggs, and you have a building with a number of floors, and your goal is to determine what's the highest floor from which you can drop an egg without it cracking. Okay, so goal, or question. What is the highest floor from which you can drop an egg without it cracking? And this is a very idealized experiment, so we have a number of assumptions. Number 1, all the eggs are identical. Number 2, all of your experiments are perfectly repeatable. There's no wind resistance or anything like that. If I drop an egg off of floor 7 and it survives, I could go back in time and do it again and it will be guaranteed to survive. Okay. If your egg survives, it is completely unchanged. So if it survives dropping from floor 7, I could drop it from floor 7 1,000 times and it'll survive each time. On the other hand, once an egg is broken, it cannot be used in your experiment. You can't glue it back together. Okay? The eggs are identical, and you start off with a building that has floors, number of floors, and you have eggs, number of eggs in your basket. And you want to know how many experiments are sufficient to answer this question. Okay, the question is, what's the highest floor from which you can drop an egg without it cracking? So your egg function, it's not going to give you an answer to this question because it depends on the eggs and the floors and the ground material and that kind of stuff. So we can't answer this question. What the egg function tells you the minimum guaranteed sufficient number of trials needed to answer this question. So the trials will vary from situation to situation. Sometimes from floor 7 it'll survive, sometimes from floor 7 it'll crack. But I want to know what's the guaranteed minimum number of trials that I need to run to answer this question. And also if it cracks from a given floor, it'll crack from any floor above. If it survives from a given floor, it'll survive from any floor below. Yeah, so we got physics.
Is there like a finite amount of floors to like the building?
Yeah, so your function is given the number of floors in the building and the number of eggs you have to conduct your experiments. So you only have to go up to that floor number.
It'd be kind of like log n, right? You test by bisection, something like that.
Something like that, yeah.
Obviously having multiple eggs.
Right, right. So yeah, we can take a very naive approach and take your egg and just drop it from the first floor. If it breaks, you've got your answer. Okay, floor 0 is the highest you can do. If it survives, we can take that egg to the second floor and drop it. If it survives, we can take it to the third floor, right? And when we get to, I don't know, the 8th floor and we drop it and it breaks, we've got our answer. 7th floor is the highest floor. So if we have 50 floors in our building, we know we can get there in 50 experiments. Yeah.
How is this different than high-low? This
Ah,
would be a good.
because we have multiple eggs. Okay, so let's suppose we have
The eggs at like different densities, or?
nope, the eggs are identical. Okay, so let's suppose we have 8 floors, right? So high-low would say, well, let's drop it from the middle floor. Okay, well, if you only got one egg and it cracks from that floor, you can't answer your question. Because you know that somewhere between here is the highest floor you can drop from which it will survive, but you've lost your only egg. All right, so if you only have one egg, you can't play high-low. Now, if you have 2 eggs, you could take a chance and say, let's drop from the middle floor. And if it cracks, you can say, okay, well, it's in one of these, but now you got to try this, 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 and see which one it first cracks from. Okay. On the other hand, if you drop from here and it survives, you know the critical floor is somewhere up here. You've got 2 eggs, and you've only got to decide which of these floors is critical. So I could play high-low again. I could try the middle one. And if it cracks, you know, that's my critical floor. If it survives, then I could drop it from that and see if it survives or cracks. So the number of eggs being bigger than 1 changes this. And the fact that if your experiment fails, if your guess is wrong, you lose an egg. Right? So that's different.
It's like high-low, but with extra edge cases.
Yeah, and I'm trying to think of, it might be like high-low where you're allowed multiple guesses, but you lose something. Yeah. So it's pretty weird. So we want a function that will tell us a minimum guaranteed sufficient number of experiments. And you know, we could always say, if you got 50 floors in your building, we could just say, you know, 50 experiments is enough. Okay, but we can do better than 50. Okay, as long as you have more than one egg. If you got one egg, you need 50 experiments. But if you've got 50 eggs, or an unlimited number of eggs, you can just play high-low, right? If you have at least log n eggs, you can just keep bisecting. And 50 floors, we could get there in 6 guesses, 6 trials. But when your number of eggs is bigger than 1 and less than the log of your number of floors, then it gets a lot more interesting. Okay,
So-
yeah.
Like, if you have one egg remaining, then you're always going to be doing the, like, lowest to the highest one.
Exactly, yeah. If you only have one egg left, you've pretty much got to try all possible floors, whatever your possibilities are at that point, and you got to try from the lowest up to the highest. So that as soon as it cracks, you've got your answer in that experiment.
And so it doesn't matter how many eggs you have left when you have the answer, it's just you
Nope,
did.
you're just looking for the answer, and you're looking for it with the smallest number of experiments.
Okay.
And there's no bonus for extra eggs. Or you can eat them. So we can do this recursively, and we've already come across a few of the base cases. So let's write this function. So egg takes number of floors, number of eggs. Okay, if there's no floors in your building, then your answer is 0. Okay, so this is 0 if your floors is 0 or negative. That's just kind of a degenerate edge case you might stumble across. If you only have one egg, we said it takes you, at worst, floors guesses if eggs is equal to 1. It takes you exactly 1 trial if the number of floors is equal to 1. It doesn't matter how many eggs you have, just take an egg, try to drop it from the first floor. It either survives or doesn't, and your answer is there. So those are the edge cases. Those are the ones that end your recursion. Floors gets down to 1 or smaller, or eggs gets down to 1. The general case, well, we're going to take an egg and we're going to drop it from a floor. We've got to conduct a first experiment. Okay? And what floor are we going to drop it from? Well, it could be floor 1, 2, 3. It could be all the way up to whatever the top floor is. Okay, so we want to go over from f equals 1 to f equals floors. Bless you. And depending on what our first experiment is, right, if we decide our first experiment is going to be to drop from floor 1, and then our situation will change. The egg might crack, the egg might not crack, right? But in the end, we're going to end up with some number of total experiments we had to run to answer our question. If instead we say our first experiment is going to be from floor 2, we'll get a possibly different number of experiments we had to run. We want the smallest of all these possible cases. Okay, so we want the minimum between where our initial experiment is from floor 1 or our initial experiment is floors. So we want the minimum over that range, right? So like a for loop. And we keep track of the smallest. So the minimum of the following quantity. So this is the experiment where we first drop from floor F. Okay, so the number of trials it's going to take is at least 1. That's dropping the egg from floor F. And then there's two possibilities. Suppose the egg cracks. We drop from floor F and the egg cracks. Well, now we have one fewer egg, but we also have fewer floors to investigate. We know the critical floor is somewhere between 1 and F minus 1. So we dropped from floor F, and it cracked. So the tallest we can drop from safely must be somewhere between 1 and F minus 1. But our number of eggs has also decreased by 1. So how many trials does it take to find the answer to our question if we have F minus 1 floors and eggs minus 1 eggs? We'll just use our eggs function. So one possibility is egg of floors minus 1 and eggs minus 1. On the other hand, if we drop from floor F and the egg survives, well, we know that the critical floor is somewhere up here. We still have the same number of eggs, but our number of floors has changed. How many floors are there between the top of the building and the floor above F? This is just floors minus F. So in this case, the number of trials it takes is egg of floors minus F, comma, eggs. And we need to consider the largest of those two. Because if we pick the smallest, and this turns out to be the case, our number of trials will be insufficient. So we actually need the maximum of these two values. That's the worst case number of trials it'll take. We add 1 for the trial of dropping F. This is the number of trials that are guaranteed to be sufficient if we start from floor F. Calculate that over all possible floors, take the smallest number, that's the value of your egg function. Okay, so this will be written up in PA5, but it's going to look a lot like this. It takes some thinking about. And the weird part is we're looking for a minimum over some range of F of 1 plus the maximum of these two things. Okay. That won't make any sense unless you get there through this line of thought or something similar. If you just look at this, it's going to not make a lot of sense. Okay, but that's the intuition behind the function that solves this problem. Yeah?
Are we assuming that eggs will never be 0 in the edge cases?
Yeah, if the eggs are 0, you can't solve the question. So let's always call the egg function with at least eggs equals 1. And, you know, when you get into there, it doesn't matter how many floors you have, you can come up with an answer without recursing. So yeah, we can assume the eggs is positive. And floors is bigger than or equal to 0.
Is this the entirety of the effect? Just one recursive function?
It's one recursive function and then a simple main program that says how many floors, how many eggs, and it prints out the answer.
Okay. And
So.
what determines if the egg breaks or not?
Don't know. Like I say, we're not actually answering the question. We're saying what's the minimum guaranteed number of trials that we need to answer the question. Right? But we can't actually find the answer, and we can't return what the algorithm is for getting that answer because we don't know if the eggs break or not. All right, cool. I will see you tomorrow then. Good luck finishing PA4 if you have not already finished it. And shoot me a note if you get really badly stuck.